Hi everyone, this is Amir here at Civil Engineering with Amir. Today we're going to solve a question from Craig's Mechanics of Materials or Solid Mechanics on the topic of axial deformation for non-homogeneous cross-sections. But before we read the question and solve it together, I want to ask you guys to hit the subscribe button and support us by subscribing to the channel. Let's read the question together. Here you can see a bimetallic bar, which is made by two homogeneous rectangular bars with different materials. These two metallic bars are bonded together at this cross section. The modulus of elasticity of this bar is 70 gigapascal. And for this one, E2 is 210 gigapascal. The length of the bar is given to us, which is 1.5 meters. The width of the bar is also given to us, which is 50 millimeters. The thickness of bar number 1 is 25 millimeters. And for the second one, it's 15 millimeters. An axial force P with a magnitude of 48 kilonewton is applied to the ends of the bar. So here and here at y equal to yp and z equal to 0. So this is our axis z, and this is z equal to 0, and this distance is yp. This is our axis y. And because of applying this load P, the bar undergoes axial deformation. Now in part A of the question, we have to determine the normal stress in each material, sigma 1 and sigma 2. And in part B, we have to determine the value of yp. And finally, in part C, we have to determine the total elongation of the bar. Okay, let's start solving the question. First of all, the bar is said to undergo axial deformation when the load P is applied at this y equal to yp and z equal to 0. So we can conclude that the strain is constant on every cross section for this bar. So epsilon x is constant. Also, since the bar is prismatic, meaning that the cross section of the bar is constant, and load P is only applied at its ends, we can say epsilon x is equal to an epsilon which is constant for the entire bar. So this is just an assumption. And now since we have two different materials, we're going to have two different values of stresses in these two materials. So if this is our bar, the thickness of the first material was 25, and for the second one it was 15 millimeters. So 25 millimeters, this is going to be 15 millimeters. This is our material number 1, this is number 2. And now for the first one, the stress will look like this. So we're going to call this sigma 1. And we know sigma 1 is equal to E1 epsilon. And sigma 2 is equal to E2 epsilon. And since E2 is bigger than E1, this sigma 2 will also be bigger than sigma 1. So sigma 2 will look like this. This is sigma 2. And now each of these stress distributions are going to create a resultant force at the centroid of their corresponding material. So for the first material, we're going to have a force like this, which we're going to call P1. And for this one, we're going to have a force like this, which we're going to call P2. So this is going to be our Y1. And this one is going to be our y bar 2. And these are the centroids of material number 1 and material number 2. And for the other side of the cut, we can draw something like this. And we're going to have a single resultant force, which is our force P equal to 48 kilonewton, and is applied at YP. And now we have to determine the value of this YP, which is actually the centroid of the whole cross section, the values of these stresses, and the total elongation of the bar. Now for part A, in order to determine sigma 1 and sigma 2, we can write the equation of equilibrium in the x direction. So we have sigma fx is equal to 0 in this direction. So P1 plus P2 minus P is equal to 0. P1 is sigma 1 A1, P2 is sigma 2 A2, and P is 48 kilonewton. This A1 is this thickness multiplied by this width, so the area of the cross section for material number 1, and A2 is this cross section, which is T2 multiplied by this B. So here we can write sigma 1 A1 plus sigma 2 A2 is equal to 48 kilonewton. Sigma 1 is E1 epsilon, E1 epsilon. A1 is T1B plus sigma 2, which is E2 epsilon, multiplied by A2, which is T2B, is equal to 48 multiplied by 10 in the power of 3 Newton. E1 is 70 gigapascal, or 10 in the power of 9 Newton per square meter, multiplied by epsilon, multiplied by T1, which is 25 millimeters, or 25 multiplied by 10 in the power of negative 3 meters, multiplied by B, which is 50 millimeters, or 10 in the power of negative 3 meter, plus E2, which is 210 gigapascal, epsilon, this is 15 multiplied by 10, and this is 50 multiplied by 10 in the power of negative 3 meters. This is equal to 48 multiplied by 10 in the power of 3 Newton. So 87.5 multiplied by 10 in the power of 6 epsilon plus 157.5 10 in the power of 6 epsilon is 48 multiplied by 10 in the power of 3. And this will give us an epsilon equal to 0.19591837 multiplied by 10 in the power of negative 3. And now sigma 1 will be equal to E1 epsilon, or 70 multiplied by 10 in the power of 9 Pascal, multiplied by this value, which is approximately equal to 13.71 megapascal. So this is our sigma 1. And for sigma 2, we have E2 epsilon, or 210 multiplied by 10 in the power of 9 Pascal, multiplied by this value, which is approximately equal to 41.14 megapascal. So this is the value of our sigma 2, and we have determined the two values asked in the part A of the question. And now we can move to part B. Now, in the second part of the question, we have to determine the value of this yp, which is the location of the centroid of our cross section. So if we assume that the centroid of our cross section is located at this point O, we have to determine the coordinates of point O. And in order to determine the coordinates of point O, we can write the equation of equilibrium for the moments at this point, which we call point A. So we will have sigma ma is equal to 0 in this direction. So P1 multiplied by this distance, which is y bar 1, plus P2 multiplied by this distance, which is y bar 2, minus P multiplied by this distance, or yp, is equal to 0. So I'm just going to copy this part. So this P1 is sigma 1 A1. This P2 is sigma 2 A2. This P is 48 kilonewton. Y bar 1 was this distance, which is 15 millimeters, plus this distance. And since the cross section of each of these bars are rectangle, this distance is going to be in the middle of the section. So this will be 15 plus 25 divided by 2. And y bar 2 will be the middle of this length. So it's 15 divided by 2. So 25 divided by 2 plus 15 millimeters. And this one, 15 divided by 2 millimeters. So sigma 1 was 13.71 multiplied by 10 in the power of 6 Pascal. A1 is 25 multiplied by 10 in the power of negative 3 meters multiplied by B, which is 50 multiplied by 10 in the power of negative 3 meters multiplied by y bar 1, which is 27.5 multiplied by 10 in the power of negative 3 meters. And P2 was 41.14 multiplied by 10 in the power of 6 Pascal. A2 is 15 multiplied by 10 in the power of negative 3 meters multiplied by 50, 10 in the power of negative 3 meters multiplied by y bar 2, which is 7.5 multiplied by 10 in the power of negative 3 meters minus 48 multiplied by 10 in the power of 3 Newton multiplied by yp is equal to 0. So 471.43 plus 231.43 minus is equal to 48 multiplied by 10 in the power of 3 yp. And this will give us a yp approximately equal to 0.01464 meter, or yp will be approximately equal to 14.643 millimeters. And finally, in the last part of the question, we have to determine the elongation of the bar. And we know elongation of the bar, or E, is equal to epsilon multiplied by L. So epsilon is here, L is 1.5 meters. So our E will be equal to epsilon L, or this value multiplied by 1.5 meters, which will be approximately equal to 0.294 multiplied by 10 in the power of negative 3 meters, or our E will be approximately equal to 0.294 millimeters. That's it. So in the first part of the question, since it was said that the bar is undergoing axial deformation, we use this assumption, and based on this assumption, we determine the values of our stresses in bar 1 and bar 2. And the next parts, we use these values to determine the value of yp and the total elongation of the bar. Thanks for watching this video. I hope you found it helpful. If you liked the video, please press the like button. If you have any comments, questions, or feedback, please feel free to write for us in the comment section. And finally, if you haven't already subscribed to the channel yet, please press the subscribe button and support us by subscribing to the channel. Thanks again for joining me today, and see you in the next videos.